Hey y'all, I'm David, and this is Lab 4 Magnetic Braking with Faraday's Law. Okay, so for our introduction, in this lab, we wanted to collect the time data on a bar magnet falling through a conductive tube, observe how the induced current in the tube affects the time required for the magnet to fall, and then finally create a computational model. For a quick preview of the results, the observed time I got was 1.02 seconds, and the computed time was 2.192. Our fundamental principles that we're focused on for this lab are the Biot-Savart law, Faraday's law, and Newton's second and third laws. And here are those. So Biot-Savart, Faraday's law relates our EMF to the change in flux. Newton's law uh, states that our change in velocity is based off of our net force, and then Newton's third law is every action will have an equal and opposite reaction. Okay, so for the experiment, some assumptions that we made were that the bar magnet acts as a dipole and that air resistance is negligible, as well as friction. The system was the bar magnet, and the surroundings were the earth and the tube. The observations. So here are the times that I got for my trials, and 1.02 was the average length. And then the tube width, length, and radii, as well as the mass of the magnet and its dipole moment. So for the code, uh, here we're just initializing some properties of the magnet and surroundings. And then here we're calculating the flux and using that to calculate the current that will be induced in the ring, as well as the net force that's going to be acting on the magnet. And here's a graph of the velocity versus time that I got. So as you can see, right here, our velocity remains constant, and that is the force of gravity and the force from the induced current um, evening out. So there's no change in velocity on the magnet, and then the time in the tube. The potential errors for this lab, there could have been errors in the time recording as well, uh, as well as in calculating the dimensions for the tube or the magnetic dipole moment. And also, our model does not account for air resistance or friction, which are going to be there in the real world. What if the resistivity of the conductor were reduced as close as possible to zero? So the current induced in the tube would be much larger, causing the magnet to fall slower. Oh no, that's not a period. Um, what if there were holes or slots cut into the tube? There would be fewer complete rings of current, so the magnet would end up falling faster. And yeah, thank